Great. Well, welcome back, everybody, for another session of the Machine Safety Workshop. This is going to be part 3 of 5. We're going to talk about the risk reduction methods and the safety functional requirement specification as we continue our path around the machine safety lifecycle. Previously, there's been some handouts sent out. Mike's going to send some of these out later as a follow-up as well. But if you're following along and taking notes, you see that D plus V plus S greater than R equation up there. That's the change equation. There's a note sort of taking little tool that got sent out earlier as well, that and basically the way to help you capture these elements of change. That equation basically is a bit of a review here. Is dissatisfaction plus a vision plus steps to get there have to overcome the resistance to change. So you see that in the notes section here that there are 4 columns to capture your thoughts and ideas as you're following along in this presentation. Some things may come to mind, specific things that are pertinent to your location about dissatisfaction with the current state, visions you might have for the future, steps you might be able to take, and some areas to note of resistance to change as well. So you can just formulate your thoughts on that as well. There's also a document I authored here that basically is an overview of the machine safety lifecycle, the reasons, the steps, and how some of it is in terms of how it can impact your businesses there. There's also a brochure sent out about integrated mill systems, machine safety, integrated safety solutions. That's my current employer. We're a machine safety integrator. But basically, that's part of our larger scope as a controls integrator, primarily focused in the metals industry, but are expanding out beyond that as well. So, and then you have the presentations to go along with it. So, anyway, here are the 5 parts. As you can see, we've completed the first 2. If you were lucky enough to be able to join us for those, the idea is that this builds upon each other. So we talked about societal demands, and then put the next portion of it, the regulatory compliance and laws and rules and stuff, in the context of those societal demands, society including industry and workplace as well. And then we also talked about the risk assessment. So, as you look at the machine safety lifecycle here, it is a 5-step process here, and each step builds upon each other. So in today's session, we're going to build upon session 2, where we've done the risk assessment. Now, what do we do about it? I'm going to tease you a little bit about what's to come after this session. Next week, we're going to get into sort of some deeper dive of the engineering controls, particularly the minor servicing exception, and even specifically machine safety circuits as well. Just not that you're going to, as safety professionals, design those things, but it might be something interesting to your engineering staff. And at a minimum, it gives you an understanding and appreciation for what a machine safety integrator does, and what is involved in creating a safety circuit. And then the last session will cover validation, and what do you do after you install all these solutions? How do you manage them as well? So today, the assumption here is we have completed the risk assessment. Now, what do you do with all that risk that you've attained or understood? You've identified the hazards. You see how people are interacting with them. You get the subsequent risk level as we measured in the risk assessment. So how do you know which mitigation solution best fits the scenario in which you are faced with? How do you most and effectively mitigate risk to an acceptable level? And then finally, how do you document all of that so that it can be designed and what you want actually gets created? How do you convey that to the design engineers who may or may not have been involved in those discussions about the specifics of what we're involved trying to accomplish? So here's an example of a risk assessment. This is the template basically that we'll follow. If you did a risk assessment with integrated mill systems, you would get a nice Word document report with an overview of the hazards in the machine and lots of detail. The meat of it is this risk estimating scoring sheet, if you will, the risk score. There we captured each of the line items here, which is the person, a task, the step in a task, and the associated hazard they'll come in contact with. That creates a line item. We would measure risk potentially up to 3 ways. But when we look at existing measures in place, we would sort of categorize or describe what's in place to mitigate the hazards that are underlying the initial risk here. And then we've also started to talk about the solutions. Hey, we've measured this risk. We found maybe the existing scenario here is unacceptable. And what are we going to do about it? So we started describing these in a very general sense. They can be very specific, or they can be very general in terms of a list of, hey, I'm just going to put, a light mat or a safety mat there, or a light curtain, or I'm going to use PPE. But you can also get very specific into these areas as well, but still not specific enough to go ahead and design it. So again, the large question here is, well, what do I do about all of these risks? Where do I start? There's endless possibilities, but which one is appropriate? The first kind of general concept along as we're going through the flow of risk remediation here is to determine whether or not we can get into which classification. There are 3 classifications of risk mitigation according to the standards. Again, this is ANSI B11, which is very much harmonized with much of the global standards that are out there. So these are pretty well accepted. The concept of inherently safe by design, engineer controls, and administrative controls. So we'll try to determine just generally which one we can do. And there's introduce this concept of most and least effective. This is the term of the hierarchy. Where can I start? The elements of what make these at the top more effective than these ones down here at the bottom. They're kind of 2 elements. The first of which is the can I affect the severity of what's going on? Can I actually reduce the severity versus the probability? When you look at some of these charts here, kind of describes, what am I actually trying to affect in terms of lowering the risk, which is the combination of severity and probability. Or am I going to address the severity, or am I going to try to address the probability? In the upper ones up here, I'm trying to do that. So can I affect the severity? The second element then is less reliance on the human factor, human performance factor. So the higher I am in the hierarchy, the less I am relying on a person to follow a process or a step. So obviously, if I've designed it out, there's the hazard is eliminated. I'm not relying on people at all during their normal operation and interfacing with what would have been a hazard. It's pretty much gone. But when I get down to these lower ones, there's an increasing reliance that people would actually do the correct thing. So if we can start at the top, design it out, that's the best. If I can use an engineer control, that would be the second best. And if at all, I have to rely on administrative controls, and rely on human performance, then, that's so be it. That's what I have to do. Also, one other thing is I can layer these as well. I don't have to just have one, but I'll probably have a primary one. What is my primary means of reducing risk? And there'll be some restrictions to that. We'll talk about here in a moment, but the main idea is try to use the most preferred or most effective starting at the top. The other thing to keep in mind is that OSHA really has 2 primary rules. We covered these last couple of times, last sessions, that really dictate if you're going to access the machine, you lock it out. If you're trying to prevent people from accessing the machine or a hazard, you use hard guarding or fixed guard. So those are the 2 basic fundamental default mitigation solutions that OSHA will look for. And subsequently, if those are inadequate or not done properly, those would be the subsequent citations and potential fines that would be associated with it. Those are the 2 main ones that you'll see. We'll also get into this concept of minor servicing exception. This is such a big topic. We're actually going to cover this in depth in the next session, but throughout this session today, I'm going to tease you and introduce you with some of the concepts in here too. But the first real question, we go back to the risk assessment, and we are going to continually bounce back to that risk assessment to ask questions or get answers to questions we might have about what's appropriate. The first question really comes to, is this maintenance task, qualify as a minor servicing task? So if it's a maintenance task, we're locking it out. If it's a minor servicing task, we had a few more steps to go through whether or not we can use that, but that's basically where this will come into play. If we're looking for further refinement of what are the possibilities, here's another, this is the standard in which the default standard, and probably the most popular standard today for risk assessments out there. It's the Robot Industry Association Risk Assessment Standard, TR 15306, last updated in 2016. Incidentally, there is a plan. This is in process now to update and further harmonize this particular standard. This 15.306 is going to be updated. It probably won't be published until sometime in 2023. But basically, what we've seen here is we've gotten the risk rating or risk level from our risk assessment, and according to the RIA standard, we're somewhat limited and restricted as to what can be our primary risk reduction measure here. As you can see, I'm going to have to use some sort of engineering control or inherently safe by design solution to all this stuff. If I've got a very high, or medium, I cannot rely on human performance if I've got even as low as a medium type of risk on here. Now, I still can, as I mentioned, you can still layer those on top of that. We talk a lot about standards. They are the go-to place to go find answers if there's any questions about what is appropriate and what is not. This is a list of I would say the core library for people involved in machine safety. The go-to answer books for mitigation in here are the ones I've circled in here too, and primarily the ones that the first one that I go to is the ANSI B11.19, last updated just a couple of years ago. Huge expansion and encompassed a lot of what's in these other ones here as well. So that's one of the nice things about the ANSI standards, is that they continually expand them and harmonize them with the rest of the global ISO or ANSI, ANSI standards or IEC standards that are out there. So we'll talk more about these. But ultimately, at this stage in the game, we've done the risk assessment. The next thing that we're going to produce is a safety functional requirement specification, the SFRS. This is a very detailed document that is going to have enough information in it for a design engineer to create the solution. And this can also be a bid document as well, to say, this is exactly what I want. So it's the mechanism in which to convey what the safety committee and the people in the team-based risk assessment discussed about, hey, what are we going to do, and taking into consideration all of the information that was available at the time, and gone through and said, okay, here's exactly how we're going to solve this thing. If the design engineer was not involved in those discussions, you're gonna have to start all those discussions over again, unless you have a safety functional requirement specification you can hand them, and it should be exactly what they need to know in order to produce or even propose a solution. Here's an example of the detail that would be in something. This would be an example of if I'm going to use a safety function or a control circuit as the primary means of risk reduction. But I'll have the details about the specific use of that control circuit, what triggers it, what is safe state, how fast does the machine have to react, how fast does it take to get to safe state, how am I going to be able to diagnose this thing, is it actually working? And we'll see later, especially in the next session, we'll get into circuit performance and the quality of the circuit. There's a a significant variety of ways that a control circuit can be designed if you're following the specifications, and it's dramatic difference from the lowest to the highest level. How good should this circuit be with duality, dual channel stuff, diagnostics, and long-term performance of it? And so there's the very, all the calculations for stop time and stuff like that. All of that's going to be defined in this as well. So here's basically the rest of the session here. We're going to talk about these in order. We're going to go through each of these classifications, and we're going to concentrate on these you see on the left, or we're going to get into some detail. But before we do that, if you're lucky enough to be involved in the design or the redesign, if as a safety professional, if you can inject, I'll say, safety into the design process, and try to attain this inherently safe by design. It's typically going to be something that would have to be done at the very beginning of the project. Here's a chart, some guidance about when safety should be infused into the discussion, and so you can see sort of risk assessments done at the very beginning, even the conceptual stage of this. And ask questions, does the person really need to be involved in this specific task? Do they really need to be exposed to those hazards? If I can figure out a way and design out a way that I don't need to have a person interacting with a particular hazard, that's probably the best way to do it. The interaction between the user who's going to say buy the machine or the system and the people building the machine, a machine builder or an integrator, involved in this. Usually that has to be worked out in the T's and C's and the contractual obligations to say, hey, we're going to have these meetings. We want to review, at these particular milestones, we want to do a preliminary risk assessment. Let's look at, see if we can design this stuff out. And if we do find something that we don't like, we have the ability to enforce going back to the machine builder and saying, you got to go make some changes to this thing. So right out of the standards there, some of the ideas of what can be done, examples of what can be done. Very common one, in heavy equipment, heavy machinery, it has to be lubricated quite a bit. That does a lot of times force people to get close to the machine to lubricate bearings and whatnot. So one of the ideas we do often is relocate the lubrication system, tubes and refilling tubes and whatnot, the Zerk fittings, put them maybe outside a physical barrier, outside of a safety fence. Of course, if you can replace a person with any sort of automation, make it remote. And then some of the other ideas in terms of substitution, maybe we don't need to use some particular product or raw material or something like that. Maybe something else can work, in its place. Or maybe the introduction of a new product, into a system, requires now further human interaction and collaboration. So an example, I work with Procter & Gamble on some systems, and they tell a story about purchasing, went out and found a cheaper material for some packaging. I can't remember whether it's plastic or paper, but although it was a less expensive, product that they could use, it was jamming in the machine, requiring people to go in there and actually, free these jams up. So they were introducing risk, which was, more cost of, it was more costly to expose associates to that risk than it was the savings for this raw material. So they went back to it. So the other thing is then, also taking a look at the process, the system itself, making sure that we're not using excessive amounts of force or pressure or temperature, if we refine those properly. Obviously, all of that is great if you can jump into the system before it gets designed, but a lot of times you can't. Or if you're involved in it, in the design, and you suggest something that is going to mitigate risk, but it may cost more, the return on investment is going to be, something that will have to be discussed as well. Can this process be performed at an acceptable level of risk, and what would it cost to get there? So, that has to be part of the weighing part of it. We talked about that, I think, in the second session, or maybe the first session there, about return on investment. But here's some further details about what could be done to eliminate risks while you're trying to design this out. Some of the other ideas is positioning of operators. If I can put them out of harm's way, move them back, maybe 2-3 feet could make all the difference if something occurred, not just in normal production, but also in abnormal operations. During this process of the risk assessment, we would ask those questions. What ifs? What if this broke? What if this piece of equipment malfunctioned? And we really should address the risk along all of that, because the vast majority of safety incidents occurs, outside of normal production. It's so close to 70% of the time a safety incident occurs, it's during non-normal operation. Something went wrong. Okay. So some of the specifics, just right out of the standards, there's been further refinement. In fact, the ANSI B11.19-2019 version of it gets into specifics that involve common aspects of human physiology, the average size of people. Obviously, this isn't going to affect everybody, but if you're a thicker or thinner person in here, some of these dimensions might be a little bit different. But they have gone through some of the elements to determine, what are the minimum and maximum gap sizes to prevent human injury. So, a good one here is an example. Here's the minimum gap. You're determining that, if it's a 1/4 inch or less, it's pretty tough to get a finger inside a 1/4 inch, and you're not less likely to get, pinched if it's that thin. And maximum gaps are minimum gaps in terms of the size of moving parts between it. So if these two are moving together, what's the minimum gap required before a human body gets crushed? So some of those studies have been done and give you some very specific dimensions, exact to the millimeter or fraction of an inch. So all that's great. As I said, if you can get into that either before, during, commissioning, or whatever, the farther down you go in this process, probably the more expensive it's going to be to re-engineer something versus catching it, early in. So there's quite an incentive for the safety professionals to be involved at the very beginning of the conceptual conversations between the suppliers and the users. So that's probably the key takeaway. It's never too early to sort of inject yourself as a safety professional into some of these machine designs. Okay, so with that, inherently safe by design, we've either eliminated or reduced the consequences of a risk entirely. We're going to move on to the next session in here. And as we mentioned, here's where OSHA, I guess, will influence, what we're going to be doing here. Let's talk about the one at the bottom here. I'm sorry, not at the bottom, but the next one down the line. The most basic, one of the most basic ones is machine guarding. It's actually classified in the engineer controls, but these are, again, fixed guarding. So let me clarify something too. Some of the most recent changes in the machine safety standards is some terminology here. We no longer are using the term safeguarding. So if you have safeguarding in your standards or your specs or something like that, that's been eliminated from the standards. So because it was confusing, safeguarding sounded like guarding. And what are you talking about, a guard, or are you talking about a machine control and calling it a safeguard, or so anyway, the term guarding, safeguarding has been eliminated, and now it's simply gone to guards specifically. So if you hear the word guard, that's what you're talking about, a physical barrier. And you'll see these as a couple of them. These are another term that you might hear is separating guard. A guard is a guard. They used to be called separating and non-separating guards. A non-separating guard used to be a light curtain. That term has been eliminated as well. So when we talk about the guard, it was formerly referred to as a separating guard. So now it's just called a guard. So now we have two types of guards, the fixed guard and the movable guards. When we're using movable guards, these are things that are easily movable, not requiring a tool, but a lot of times this will involve the integration of a movable guard with the control system as well. So a gate, for instance. Okay. And obviously, here's the purpose of the guard. Again, it's pretty basic, and this is probably one of the areas, if you go to the OSHA regulations, CFR 29, Part 1910, you'll see specific references to guarding, more so than just about anything that's in that section of the law. But these are the objectives that you'll see coming out, and they're also, infused and used throughout the standards as well. These are what we're trying to affect. Ultimately, the caution with guarding is that a lot of times a guard will be put in place, and boy, okay, now you're safe, but you may have made the person's work harder, or maybe impossible to do. So what will happen with that is it invites or induces a person to defeat those guards as well. So we may think we'll put a guard in place and we're going, hey, we fixed it, but you also may have introduced a reason to defeat that, which ultimately is less safe, because somebody's gonna take that guard off because they simply can't do their job. So when we're designing guards, that's probably the most important things, to make sure that we can actually, continue to do the job. ANSI B11.19.20 also very much references the previous standard that was used, is this ISO 14120. And 14120 pretty much has been totally absorbed into 1910. So there really isn't, sorry, that's a typo there. It should just say B. I fat fingered that, sorry about that. But ANSI B11.19 should be really the only machine safety standard that you really need to follow, and it pretty much takes care of the rest. So you can see some of the specifics called out, when we're talking about a fixed guard. The ones that probably everybody knew, it takes a tool, for instance, to remove it. The other thing to think about is this acronym of AUTO. When the guard is in place, I'm unable to reach around, under, through, or over. The physiology is standard human physiology. That's referenced in the standards out here, but you'll see tools like this, referred to as a gotcha stick, that will be used to test this auto concept here. I can't get around, under, through, or over, and this will not only reflect a human physiology of it, thicknesses of fingers and hands and reaches and arms and stuff, but those dimensions are all laid out in the standard as well. Great. Okay, so that's guarding, pretty brief. Next one we're going to go to is the other concept, sort of default standard here, is lockout tagout. This falls in the hierarchy classification as administrative controls, where we may put these means of isolating hazardous energy in place, but it takes a human to actually perform those. It doesn't do any good if people don't follow the procedure and stuff, or use the tool. So anyway, we're not really going to talk much about the rest of these. The rest of these are a lot of times they're outside the scope of a control company, with probably the acceptance of signaling, audible or visual signaling of it. That's another layer sometimes that are laid on top of some of the primary engineer control solutions out there. There might be a light or a horn or something like that indicating that a safety function is being triggered. But primarily, the consummate sort of default here is lockout for the primary means of risk reduction, especially if it's a maintenance task. So this is the consummate standard, ANSI Z244.1, most recently updated in 2016. So this is, in fact, in North America, I don't know that there is even a rival to this standard, but this would be the lockout tagout standard that OSHA and most corporations and companies and regulatory agencies around the world, or sorry, around North America, would reference to. these are the primary components of a lockout tagout program. And these are the primary means or reasons why, if there's some deficiency in a lockout tagout program, this is where OSHA would issue fines for. So they would be, a fine for one of these elements here that's somehow deficient. You don't have a proper audit program, or we don't have in fact, the most common one is not having a procedure for every machine, that's out on the floor. That is a requirement. Employee training is another big one too. Improperly trained people or unauthorized persons using or misusing lockout tagout properly. So when do you need to do lockout tagout? It's pretty much every time somebody's going to access a machine. And we'll talk about the minor servicing exception next, but the default is if you're going to clear a jam, if you're going to lubricate a machine, if you're going to access this machine for any reason, the default, the first step is lockout tagout. And there should be a lockout tagout program for every machine that's out there, a procedure, and have it well documented and well illustrated. When do you not need lockout tagout? When is lockout tagout not employed? And you can see the first one here is typically when it's a corded product. This only obviously adheres or it is applicable to electrical type of machinery, but there's rules about that too. If it's a corded product, the end of the cord, the plug that's unplugged laying on the floor, must be in sight of the person, or the person must be in sight of that plug, or whoever might walk over and see that plug and go, oh, hey, this thing is unplugged. Let me plug it back in. They should be able to see where the person is working. If that's not possible, we want to have something that will allow that person that's in the machine exposed to the hazard to have what's called exclusive control. So there are tools of which we can use. The exclusive control here would be effectively, I put this cover over the plug here, I lock it, and then this key remains with the person who's actually doing the work. It's in their body, in their pocket or something like that. They're hanging on to it. That would be called exclusive control. So, and then the other one, again, another T-store minor servicing exception, is if you can justify using minor servicing exception and you've done a risk assessment, then I can get away with not locking out, allowing access to that machine with energy still available in the machine. I can expose people to hazards that way if I followed all of these rules, and we'll cover these in depth, but this would be during normal operation. The activity is routine, repetitive, and integral to the operation of the machine. Whatever alternative measures I use to mitigate that risk has to be just as effective as if I did lockout, tagout, or if I physically guarded it. I cannot increase the risk. And then we'll talk about how justification of minor servicing exception gets done as well, but that should be documented as well. Just to touch, a little bit more on lockout tagout here. We're talking about hazardous energy. What is the hazardous energy that we're really talking about? And a lot of times we think about lockout tagout as simply the electrical lockout tagouts, but there's a number of other sources of energy that can cause harm to people, as well as you can see, not just electrical, but the hydraulics, pneumatics, thermal, all of these sources of energy in here too. And they're categorized as lockable or non-lockable. Some of this hazardous energy is not lockable. The ones that are lockable typically are the ones that we pay for to produce. You heard the term wages, water, air, gas, electric, steam. Those are the ones that typically there's some sort of utility bill or some bill, internal bill, that it takes to produce those kind of energies. But those are the lockable sources. The non-lockable sources are typically these, where there's a lot of times it's residual energy that might be stored somehow, be it electrical or spring energy or something like that, kinetic energy, thermal. And typically there's a procedure in place that when I do the means of mitigating exposure to that hazardous energy is typically with either awareness or simply dissipation, or a combination of them. I'm aware that this capacitor has to discharge before I access this, because there's stored energy in there that can, it can kill people. Okay. The the rules, the laws, the standards say that a lockout tagout procedure should have these 8 steps in here. I'm not going to go through them individually here, but you'll get the slides later. But take a look at your procedure, compare these 8 steps, with the ones that you have there, and determine, have you adequately documented, all 8 of these steps in year 2. Probably the most important one is the test and return, where you do the lockout, you test it, you turn it back on, test it, turn it back off, test it. Again, to make sure that I've got the proper, I've isolated the proper, energy as well. Don't just lock it out and assume, hey, I've got the right one. We hear of numerous times where there's an assumption made that even the documentation might be correct. Changes might have been made, or there might be a fault, a short circuit someplace where, the last 50 times I did lockout tagout and I went to this particular breaker or I closed this valve and locked it out, that it was effectively done. And I've gone into the machine and everything was just fine without testing it. But that one time, again, outside of normal operations, something abnormal happened. I have a short circuit or a leaking valve or something like that. I locked it out, followed the procedure properly, but some failure allowed energy to continue to get past the isolation and cause some harm. So that testing procedure, well, turn it off, test it, turn it back on, test it, turn it off, test it. Did it actually, do I actually have the correct isolating device actuated? And then also the procedures should be in there on these 5 steps to re-energize something as well. So again, I'm not going to go through each one of these individually here, but you'll get these slides later. Look at your procedures. Do you have 8 to lock out and 5 to relock or to re-energize, return to normal operation? There's an argument too whether or not number 6 should be return those devices to their authorized storage location. But that is probably an added bonus. It should be done as a procedure. So add it in there if you feel like you need the number 6. Okay, so we talked about this concept of minor servicing exception. Another term for that is alternative methods. The most recent ANSI Z244.1 standard in 2016 made a major emphasis on alternative measures. This was because lockout tagout is obviously something that is going to stop the machine. And that does set up a conflict between the production and safety, elements that are out there. We talked about that previously, that dilemma that the operator's constantly in, the production pressures that are out there. So previously there was just an emphasis, you shall lock out, tag out, that is the way it is, and you shall do it. But again, where you're talking about an administrative control, we're down lower in the hierarchy of risk remediation. We are depending on human performance to do this every single time. And it's countless times where somebody says, hey, just this one time, I'm not going to lock out. I'm just going to reach in there because I don't want to sacrifice production for this one time. And that typically is when, the higher potential for an incident to occur. So there was a huge emphasis on minor servicing exception, a huge emphasis on alternative measures. So there's a whole process to go through to say, can I get to the can I get to these alternative measures? And these are there's a flow chart. We'll cover this in a bit as well. But so there was some guidance provided to say, can I use the minor servicing exception in this case? So there's again this flow chart to say yes or no. And this is a go no go kind of process here. Can I use the minor servicing exception instead of locking out or guarding? Okay, so we're going to get to the minor servicing exception. We're going to cover that in the next session in detail, but we're going to lead up to this and I'm going to introduce you to some of it. But before we do, we're going to talk about this one other one here, e-stops. Emergency stops are one of the most ubiquitous safety things you're going to see on a machine. Every machine should have an e-stop on there, and at a minimum. So there's some further guidance on how to properly, utilize this concept of an emergency stop. The guidance specific to this and is referenced by ANSI B11.19 is ISO 13850. That is the sort of the most detailed aspects that you'll find in defining what should go into proper e-stops. And again, this is every time those standards are revised, they're revised based on specific incidents that may have occurred where somebody was maybe compliant with the previous version of it, but an incident still occurred. So, where were the gaps in that previous revision of the standard? So you'll see changes. So it's important when I reference a standard to make sure that you're utilizing the most recent one, because there were significant changes. If somebody decides to republish, revise something, it was because of, had some good reasons for it. Okay, so here are the details of specifics around, emergency stop functions. The most important one is location of where they are. The purpose of it, will it prevent or impeding or stop actual, hazardous situations from occurring. It should be active all of the time. Nothing should ever override e-stop. It should be maintained until it's reset. So if you've got e-stop buttons that are with momentary push buttons, they should be actually maintained push buttons. You hit it, it sticks in there. It has to be pulled out before it can be reset. So it should somehow, when I hit e-stop, everything stops and it stays stopped in there too. It should be a single human action. It's important that the person doesn't have to contemplate. So let's say you're looking at an operator station. It should be obvious which one is the e-stop button, and they should be able to hit that without thinking, taking any time of contemplation of what can be done. Also, the repercussions of when I do hit an e-stop, what happens? I can't cause a new risk. So I can't, let's say, topple over if I'm moving product or something and it might be top heavy. I hit the e-stop, everything slams to a stop and the thing falls over and crushes something. So all of that has to be taken into consideration when I'm designing e-stop systems. It can't just, hey, let's just put a circuit in there, boom, everything stops and we're done. There has to be some further considerations, about that as well. So I mentioned location is quite important as well. So an e-stop study is something that should be done on a regular basis as well, because e-stops may have been placed based on assumptions by engineers, but then it turns out, hey, we're actually using this machine or this production line a little bit differently, and people are actually accessing it or being exposed to certain parts of it that I didn't anticipate. And those should be regularly considered and say, maybe an e-stop should be put in place here. So that it takes into consideration some of the changes that were made as well. Also, the idea of where an e-stop should be as well is it should be in places where people have access or can visually or sense something going wrong. So it's beyond just, can I see something that's going on? In some cases, maybe I smell something going on. So maybe something's burning, and something needs to be stopped. And the wind is blowing one particular direction, and maybe, an e-stop should be downwind of that. So if I do smell something or it's a leak of something, I want to hit an e-stop. So the locations of those are quite important, and it really has to do with how people are collaborating and using the machines. Just a little bit background on stopping as well, because there's some restrictions on e-stops on which we can do, but you'll have to, put these in the context of all the different types of stops. A stop isn't a stop. So there's normal stops, emergency stops, and we'll talk about protective or safety stops when we get into minor servicing exception and safety functions in there. But these concepts have been harmonized across all of the standards as well. So you got normal, emergency, and protective stops. The other thing that has been harmonized here is the category of stops. So regardless of what standard you go to, you're going to see category 0, 1, and 2 in here. Category 0 stops are where when I trigger it, I isolate the energy going to an actuator, and it's now you're at the mercy of the friction or inertia of the machine. It's going to simply, I'm going to open that up and I'm going to stop supplying energy to an actuator, and whatever happens, happens. Sometimes that's not going to be the safest scenario. So a category 1 stop might be utilized instead, and that's a powered stop. So that could be something that could, if I'm using a drive or a valve, I want to power down. I mean, I could stop a high inertia or over inertia load. I can bring it to a faster stop if the drive is still engaged. I can use electronic braking and stop it faster. That might be a safer scenario than just opening it up and letting it go. Also, if maybe I want to extend the stop, if I hit the stop and I'm moving something that could topple over, I want to extend that out so I don't cause a problem, versus maybe a high friction load. If I hit it and boom, everything stops and everything topples over, maybe I want to ramp it out. But category 1 says I'll power down to and then isolate. So versus just isolating right away like a category 0. So category 1, I power down and then isolate. Category 2, we'll talk about these. This is where the magic occurs in the minor servicing exception. And a lot of advances in technology is that I will come to a stop, typically a controlled powered stop, but I won't isolate the energy. I'll stop and I'll hold. There'll still be energy available at the motor or the valve or the actuator. Maybe I need to hold something in place. Okay. So all of these apply to whether or not they're electric or hydraulic or pneumatic or any source of energy that's going to produce motion. But the types and whatnot are also dependent. We're going to go back to the risk assessment to make a determination which we're going to use. So the only exception is I can use any of these except for emergency stop. I can't use a category 2. Otherwise, all of these possibilities are available to me when I'm considering how do I want to stop. In there, I can use 0, 1, or 2, except for emergency stops. I need to use a 1 or a 0. Also, these concept when we do an e-stop study is the span of control as well. You may not want to stop the entire production line or an entire machine. Maybe it's just portions of the machine. So how people are interacting with the machine, production considerations, safety considerations. If I stop one part of the machine, am I going to induce a hazard someplace else? So looking at the physical layout of the machine is vital. What parts are going to be stopped? What parts are going to continue to run? And also adjacent to it. So if I have 2 zones here, if I put an e-stop and I stop this zone here, what are the consequences that happen right here adjacent into this second zone here? So for instance, say this is a furnace and I've got parts that are coming out of the furnace and I open the furnace door to the second one, but somebody hits an e-stop and e-stops the furnace midway while this piece is coming out of the furnace. Well, the furnace door is open and the conveyor stops with that piece mid-stop here. I'm going to leave that furnace door open. That may cause all sorts of problems with a exposed furnace door open. So that's what we mean by adjacent hazards. Graphically, the zones should be not just with I'll say a text-based explanation where the e-stop occurs, but the standard also suggests some sort of graphic, especially if I've got a production line and I have multiple zones. I can't make an assumption that every e-stop is a global e-stop, that I hit everything. But if I have zoned my machine and I have e-stop zones, I need to graphically represent that at the actuator itself. So sometimes I'll actually have 2 e-stops for 2 separate zones on an operator station. I'll need to graphically explain, and I can add text there as well to explain, maybe the graphic. But if my e-stop is going to stop just these sections right here, and a normal stop is gonna do these here as well, I need to somehow graphically expand that as well, explain that. Okay, so there's e-stops as well. So we mentioned a little bit more of a tease. We're gonna use the second session to talk about the minor servicing exception because it is a deep topic and a broad topic, but I'll sort of introduce it to you here. As I mentioned, it's the sort of the tweener, the exception to lockout, tagout, and machine guarding. And you'll want to memorize these words in here: routine, repetitive, and integral to the operation of the machine. These are all the key aspects around the law. It's even mentioned in the OSHA regulation as well. These are the rules. It has to be to take the minor surfacing exception. I first have to ensure that this is only going to happen during normal operations, and that the task that we're going to use this for is routine, repetitive, and integral to the operation of the machine. And lastly, it does not increase the risk. So in other words, it has to be just as effective as if I locked it out. As I mentioned, the standard will walk you through this and give you some idea. Can I take this minor surfacing exception or not? So you go through this flow here, and it answers pretty much a lot of your questions as well. But I have to document this. Further, OSHA gives you some guidance as well and some case studies that are pretty interesting, where an employer took the minor surfacing exception, and then OSHA would come in this particular scenario, explain why it was ineffective, why they could not and should not have taken the minor surfacing exception. They had to do lockout, tagout, and have a citation for ineffective lockout, tagout, or ineffective guarding. So the standards, the most recent ANSI B11.0 in 2016 added this justification step in here, and a form in the annex that you can use. I've created one here for our customers and for use here with integrated mill systems that you're welcome to as well. But this is the means of which we can capture the decision of why we're using. We're not going to lock out, tag out. We're not going to use the guarding. We're going to use minor surfacing, and the elements of which the justification and what's called practicability of minor surfacing has to be documented. These are the elements that should be in there, and that annex that I previously showed you in ANSI B11.0 doesn't cover all of these, so that's why this one was created. But capture all the details about the people and the tasks associated with it, prove and show how it's routine, repetitive, and integral to the operation of the machine. Repetitive is a question sometimes about what that is. That's there's some interpretation in here, so it's best to have that clearly stated and clearly understood throughout the company. What is a repetitive task? What's a routine task? But this is a place to begin to capture that stuff too. You also have to explain how lockout, tagout has what kind of effect that has on the production. And here's your beginning of the justification parts of it. Here's why I'm not going to do lockout, tagout. It just is expensive, or somehow affects the quality of the product or something. If I have to start and stop, and I have to scrap products and stuff. So there's some aspects of practicability that come in there as well. It's going to say you should do a risk assessment. If you haven't done a risk assessment, there's at least a way to sort of document the hazards that we have come across, and what are we going to do about them. Here's how the alternative measure is going to affect that as well. So you say, here's what I'm going to propose, and here's how I believe it's going to reduce the risk. If I can reference the risk assessment that I've done, you can show that future column in there to say, look, I went from a high to a negligible because of this. This will be reflected in this document as well. And what else was considered, as well? Here's the decision I made, which a decision is the elimination of all other options. So this is where you list, though, to say, okay, we've thought about this, but this is why it was not going to work. In case an incident does occur and an inspector comes in and says, well, you should have done this. And you go, well, we thought about that. Here's why. You don't have to just make it up on the spot. Then, of course, you want to get the names and everybody involved in that decision as well, and hopefully get the highest person out there to sign it as well. So we covered everything in terms of, except for the minor surfacing exception. We're going to cover that in detail in the next session. But hopefully I give you an idea about, these categories and the hierarchy of remediation, start with the design, then move to engineer controls, and then the last one you want to depend on is just administrative controls. We're going to cover these engineer controls, these types of engineer controls in detail in the next session, next Wednesday. But ultimately at this stage, hopefully you realize too that all of these solutions should be documented in enough detail that would allow, say, two engineers to come up with the exact same solution. Okay, so that's the basic premise of and purpose of a safety functional requirement specification. And that's pretty much it. It's kind of a wrap. We've got a few minutes left here in the hour to cover this stuff, cover any questions. But next week we'll get into the, some more details about those control functions. Okay.
Yeah, Mark, I don't see any questions in the chat or Q&A function.
Okay.
Last opportunity, if there's any questions you guys want to type in there real quick. Just got a couple thank yous in there.
All right, good. Yeah, and again, a reminder too, this is an abridged version of a machine safety workshop that we offer to clients and companies that utter the words, we don't know what we don't know, or we want to get a better understanding across cross-functional people. So maybe the engineers understand this pretty well, maybe EHS understands this pretty well, but maybe operations doesn't quite get all this, maybe maintenance doesn't, maybe purchasing, maybe the plant manager. So these are, this is kind of crafted so that it would cover, multiple roles and induce conversation amongst those roles and start sharing ideas and specifics. So typically we'll do this in a, in person at your plant, or if you're near Willoughby, Ohio, we've got a very nice presentation room here. We can host it here too.
Nice. Well, Mark, we always appreciate it as usual. Great information. Again, I'll be sending those files out with the video links throughout as long as you're registered for this event, and just to get the information out there. So thank you very much. Everybody out there, thank you. Be safe.